Throughout this video, we're going to talk about the human visual system and how we can exploit it to be more sensitive to low levels of light and improve our overall viewing experience through the telescope. But first, I want to talk about John Herschel and his illustrations of deep sky objects. Just to try and give you an idea on how accurate James Herschel's drawings are, here's an image I took of the M3 globular cluster, and here's a drawing that he did of the M5 globular cluster. The reason I'm focusing on John Herschel's depictions of deep sky objects is because I believe he best illustrates what you see through a telescope. Astrophotography produces wonderful images, but the images you capture through a telescope are not the same that you perceive with your eye. Here is the Dumbbell Nebula. Now, one thing that's important when you're doing any astronomical observations is to make sure that you've prepared before time and know what you're looking at. For example, here's the same nebula as captured by the VLT. This fantastic display is the result of a dying star shedding its outer layers, effectively leaving behind a tombstone for us to remember it by. And then, on the other hand, we have stuff like the Black Eye Galaxy. The Black Eye Galaxy has this same angular size in the night sky of around 9 arc minutes, but it has a totally different story. It's a galaxy. It has 100 billion stars, each star potentially having its own planetary system, and each planetary system having its own unique history. Let's start with dark adaptation. It's one of the most fantastic features of our eyes. I mean, have you seen our eyes dilate before? You should try this experiment. Take a look in the mirror and turn the light on and off. You can watch as your pupil changes size. While the pupil dilating is one of the more visual effects of dark adaptation, it's actually rather minor in the grand scheme of things. You see, our retina undergoes physical changes when we allow it to sit in darkness. You see, when we're not providing light to the eye, the photopigments in our eyes begin to regenerate. Every time one of these photopigments gets hit by a photon, it bleaches or saturates, and it'll take a little bit of time before it reaches full sensitivity again. As the amount of time you spend in the darkness increases, the threshold of light that you can detect goes down. Now, it's a very interesting two-step graph here. You can see some rapid decline initially, followed by slower decline later on. This initial short decline is the cones in your eyes, and the photopsin regenerating pretty quickly. After that, it's up to the rods in the rhodopsin, and that takes a much longer period of time, upwards of around 30 minutes. Another adaptation of the eye is its ability to adjust its exposure time in response to low light levels. It's tricky to come up with a good measure of exposure time for the human eye, but for our purposes, let's examine the eye's response to flicker, since I find it most analogous to a camera shutter. From the graph, we can see that as retinal illumination decreases, the critical flicker frequency decreases, down to around 5 Hz in scotopic conditions. It's apparent that the eye is able to increase its exposure time, but I feel there is more at work here. I was unable to find any research, but I and others have observed a long-term integration property of the eye. When looking through a telescope, oftentimes it feels like the image builds up over a long period of time, a bit like the video in the background. Here's an anecdote from Sky and Telescope. Clark, 1994, cited O'Meara's visual recovery of the Halley's Comet after 1 to 2 hours, claiming it demonstrated a long-term integration property of the visual system. Now, along with darkness adaptation, you can also do something called averted viewing. Now, averted viewing is very interesting because astronomers have known about it for a very, very long time, but it took until 1911 when it was first characterized as the distribution of the cones and rods in the eyes. In fact, here we can actually see a plot of the cones and rods along the eye. As you can see at the center, the fovea, there are no rods. So it would make sense that if the rods are more sensitive to light, we're not going to want to look straight in the center of our vision. It turns out that 10 degrees is actually the perfect point, not the rod peak. If you look at this graph here of darkness adaptation by angle off of fixation, 10 degrees is by far the most sensitive part of the eye for low light sensitivity. Let's take a look at these two graphs. So this one over here is darkness adaptation by time in central vision, and this is the one that we just saw where it's by angle. One thing you'll notice is that after 40 minutes of adaptation time, just going 10 degrees has dropped your sensitivity from a log 2.5 microlumens to about log 1.5 microlumens. That's a 10 times increase in sensitivity simply by looking 10 degrees to the side. To wrap things up, I want to end with a quote from Robert Greenler in the preface to Rainbows, Halos, and Glories. A person who increases the number of areas in which he or she can perceive new things has a source of excitement and satisfaction denied those who do not. With this video, I hope I've expanded your ability to perceive the night sky with both the eye and mind. Thank you for joining me.